Alrighty, everyone. So we are going to be taking notes on topics 9.5 through 9.7. Okay. So let's talk through this together. So let's start on page 14. Okay. Enthalpy and entropy, and what's going on when something dissolves. Okay. So I have this model, and let me go grab some water molecules. One. Alrighty, so water, great. We have an ionic compound that's going to dissolve in water. Okay? And what's going to be happening here, so it's just kind of this stage thing. So we have this, and we're going to place it in the water. Okay? And the water molecules are going to start surrounding this solid that we've placed in the water. Okay? So it starts surrounding this guy. And notice something. Notice how the oxygen, which is the negative end, right? When we have a water molecule, hydrogen and then oxygen. Oxygen is more electronegative than hydrogen. So this is a polar molecule. It has a partially negative side and these partially positive hydrogens here. Okay. Oh, look, I broke a nail. So sad. Okay. So with this small little ion here, notice how it's the oxygen that's attracted to it. And then notice with these bigger ones, these green ones here, it's not the oxygen that's attracted to it, it's the hydrogen that's attracted to it. Okay? This must be our positive cation. This must be our negative anion. The cation is attracted to the negative side of the water molecule, and our anion is attracted to the positive side of our molecule. And what's cool is that although the bonds between these ions are really strong, that it takes a lot of energy to pull them apart, that if we get enough water molecules, if we can get enough water molecules to surround an ion, its collective force is enough to pull it off of the solid, right? And so then we can separate or dissolve, right? We can separate these ions from each other as they get dissolved in water, okay? And what we end up with is these ions floating around in the water. Wonderful. Now, a few things. First off, anytime we are pulling items apart, breaking them apart, that takes energy. We have to add energy to be able to break a bond. Okay? This is also true with like water molecules. If I try to pull water molecules apart, I have to add energy before I can pull these water molecules apart. So in both scenarios, for both the solute, what goes into the water, and the solvent, it requires energy. We have a positive delta H. It requires energy to break these items apart. So it always takes energy to break items apart, whether it's ionic bonds or IMFs. We have to add energy. And when these IMFs or bonds are formed, energy is released. So when we reform bonds, energy is released. We can hear it. It produces a sound, right? At least these models do. And the sound represents the energy that's released when those bonds are formed. So we also have, so delta H for both of these interactions would be positive because I have to add energy to break them apart. And I have to add energy to break them apart. Okay? But what about when we form a new ion dipole moment right there? that yes, it took energy to break this apart, and it takes energy to break these apart. But what about when the water molecule attaches onto that ion? Energy is released. This would be a negative delta H. Okay? Now, in addition to delta H, enthalpy, we've also been talking about entropy, the measure of chaos. So what if we go from a solid, if we go from an ionic solid to dissolved in water, aqueous, we have to pull them apart. They're further apart from each other, floating around in this water than when they were in the solid. So for just this guy, going from this to breaking it apart, this would be an increase in chaos. This would be a positive delta S to break that apart. Okay? It would also be a positive delta S if we're going to break apart water molecules. If they go from this structure to being further away from each other, where they can like move past each other, that's an increase in the chaos. The further away they are, the less ordered or the more chaotic it is. And then what about when they form? So when I break them apart, the chaos increases, but when they come back together like this, when the water attracts to the ion, it's holding it there. And so then that adds order or reduces the chaos. And so that would be a positive delta S. And so they talk about this quite a bit. What's going on with enthalpy? So let's do delta H, or enthalpy, and entropy, delta S. Okay? For the solute, and let's label each of these. So it's going to be breaking solute. We're going to break apart the solute. We're going to break apart the solvent. So we're going to break let's do break apart. Oh, is it just one P? Yeah, that looks right. Break apart solute, break apart solvent. Okay, so this is going to be breaking apart the solute. This is going to be breaking apart the solvent. And then this is going to be the solute and the solvent coming together, right? Not breaking them apart, but coming together. So let's see. Let's just call it that. Coming together, solute and solvent. And let's talk about each of these things individually. So here's my solute, and I'm specifically talking about not just staying here, not in this form, but when it breaks apart. So this breaking apart, okay? Now, in order for me to have broken that all apart, I had to add energy to it. It takes energy to break that apart. So that would mean I have a positive for my delta H. And when we break it apart, when it goes from being ordered to broken apart, then it becomes rather disordered, okay? They have a lot more movement the further away they are from each other. And so we would increase in our entropy. It becomes more chaotic. I have to add energy to break it apart, and when I break it apart, it becomes more chaotic. Now, what about the water molecules? The water molecules like each other. We got these strong London dispersion dipole, and even hydrogen bonding IMFs holding these water molecules together. And what if we break them apart so that we can fit our solute ions in there? So I'm going to break this apart and break this apart from each other, okay? Well, to break apart the solute, it's the same thing. I have to add energy to do that. But once I do this and I add that energy, now they're further away from each other. They have more movement here. It becomes more chaotic. They're taking up more overall space. And so that would be a positive delta. So here's my water molecules that I've broken apart, okay? And I'm now going to take my ions that are broken apart, and I'm going to add them together. So adding the solute into the solvent, okay? And so what we're seeing here is that, and we could hear it, that when these ion dipole interactions are forming, energy is being released. That would be a negative delta H. And they become more ordered as well as these items come together. They're less spread apart from each other. They're more orderly, and so it's less chaotic. So this would be a negative. And so when we break these items apart, we have both a positive value for the delta H and the delta S. When they come together, then we have a negative value for delta H and a negative value for the delta S. We know that if this actually occurs, if dissolving something actually happens, then it was thermodynamically favorable, and that means that our delta G was a negative value. Okay? And so there's two things to consider here, and I don't think it really dives into it too much. Just a reminder that delta H, when it's negative, it's pushing favorability, it's driving favorability. And so if this can outweigh these ones, then that is pushing it towards being thermodynamically favorable. I'll also tell you that this is often not the case, that usually when something dissolves, the delta H is positive, that it's endothermic typically. And then delta S is positive. This is going to drive this as well, okay? And so what we have here would be that these positives outweigh the negative that's created when those ion dipole interactions form. That if these outweigh that for this entire interaction, then overall we'll have a positive delta S. And usually when something dissolves, that is true. That is the case. And so I will say that this is an ideal scenario, right? That our delta H is negative and our delta S is positive. Usually when we're dissolving something, the delta G tends to be negative. A lot of things tend to dissolve, but if it didn't dissolve, it would be a positive delta G. And usually when we dissolve something, it's a positive delta H, and it's a positive delta S. Now this makes sense if you think about it, because if I try to dissolve something and it's not dissolving, what's one way that we could push it to be thermodynamically favorable? How could we push it to actually dissolve? And that's increasing the temperature. Well, guess what? If they are both positive, then it's going to be thermodynamically favorable at high temperatures. So that's another thing that supports this idea that dissolving something, tends to not occur at low temperatures, and it does tend to occur at high temperatures. And so that would suggest that usually our delta H is positive and our delta S is positive. Okay, great. Here's another concept. We've discussed this before, that if I have a base reaction here, okay, and I'm just calling this reaction number 1, that this reaction number 1 can have a delta H, like we can have a delta H for reaction 1, when we can have a delta G for reaction 1. Like we can have actual numbers for our enthalpy and our Gibbs free energy. And then we can also have K values for reactions as well. Okay? That all of these can be present for every reaction. What if I take a reaction and I take the opposite, the inverse of it? Okay? So for this, what I need you to know is that to solve for delta H2, you would do the negative of delta H1. Okay? that when you take the inverse of a reaction, then the delta H would become the negative of what it was before. And the same is true for delta G. I should have written it smaller, I apologize. The same is true for delta G, that delta G for reaction 2, so delta G2, is going to equal the opposite, the negative of delta G1. Okay? That's why I put these ones in the same box, by the way, is because they're going to be consistent. That if we take the inverse, the opposite of a reaction, then we have the negative of the delta H and the delta G. But K values were different. They were funny. To solve for K2, to go from this reaction to this reaction, instead of doing the negative, you do 1 over the K value. Okay? Now, what about if we're going from reaction 1 to reaction 3? If I want a delta H for reaction 3, reaction 1 and reaction 3 are exactly the same, except this one was multiplied by 3. And so what's really nice about our delta H values is if we multiply a reaction, we multiply the H values and the G values. So if I do 3 times by delta H1, then that will equal my delta H3. Okay, let's see if I managed to squeak enough room in here. Same thing is true for delta G. So delta G for reaction 3 is the same. It's 3 multiplied by the delta G of reaction 1. So if you multiply a reaction, you multiply your delta H and your delta G values. K was different though. Instead of multiplying your K value, even though the reaction multiplied, what you do is you take the original value and whatever it was that you multiplied it, you raise it to that number, right? So what if we want to take 2 reactions and we're going to add them together to get an overall reaction? What if I have reaction 1 and I want to add it to reaction 2? Okay. Reaction 1, I want to add it to reaction 2. Well, the first thing I need you to know is that if something shows up on both the product and the reactant side, then it's going to cancel. So here's an example. See this 3H2 on the reactant side and 4H2 on the product side? These 3 will cancel with 3 of those, leaving 1 left over. And see how we have methane CH4 on the reactant side and the product side? Then that would cancel. Everything else is still there though. So my overall reaction, I'm going to call this reaction 3. My overall reaction would be carbon monoxide gas plus 2H2S gas results in, double arrow, CS2 gas and our H2O gas. All right, that would be my overall reaction. Well, what if I want to solve for my K3? I know what my value is for K1. I know what my value is for K2. But how do I figure out what this K3 is? Well, when you add reactions together, the K values multiply. So this would be K1 multiplied by K2. And so K3 would equal these guys multiplied together. I'll grab my calculator. I don't know where my good calculator went. All right, use a different one. So, you can just plug it into your calculators like this. If you're multiplying numbers in scientific notation, a way to do it without a calculator is that you multiply the coefficients. So you can do like 9.17 and times it by 3.3. And so this would be 30.26, etc. And then you do times by 10, and then it's the exponents added together. So -2 plus 4, and so then that would be a 2. Okay? And proper scientific notation would just have a single place, like we'd move this over, we'd have one digit in front of the decimal and then any number after that. And so it'd be 3.026 times by 10. And since we made this number smaller, that makes the exponent bigger, and so that would turn into a 3. So that our K3 value equals that. All right, great. So K values, when reactions add, K values multiply. But there's my K value. But what about my delta H? What if I want to solve for delta H of this third reaction? Now, instead of, we added the reactions together. Instead of multiplying our H values, they add, which is so nice. It's a lot more logical. So delta H1 plus delta H2. Okay? We simply add them together. So then delta H3 would be these values added together, -206.1 plus 232.5. They're both in kilojoules, and so we have 26.4 kilojoules. When you add and subtract numbers, your final answer should be the least amount of digits after the decimal. So they both had one digit after the decimal, so that would be my answer. This one we multiplied, so it should be the least amount of sig figs. So really my answer should be 3.0 times 10 to the third. All right, and then finally our G values. Gibbs free energy is really similar to delta H. So because we added delta H values together, we also add G values, delta G values, Gibbs free energy values together. And so delta G3 would equal negative 54.7 plus 1.4, and so we get negative 53.3 kilojoules. That's our answer for that. So we've discussed the differences between delta H and delta G's when we're manipulating reactions, and then when we add reactions together, we see that we would add together H values and G values, but we multiply K values. All right, last concept. There's a relationship between delta G and K, and these equations are in your blue reference guide. But what I need you to know is that you don't have to actually calculate with these. We just have to understand this relationship. How can we relate delta G to our K? All right. So here we can see that the larger the K value is, the more negative our delta G will be. Okay. And we do have this more or less this tipping point here, and it's the line is when K is equal to 1. So when a K value is larger than 1. And we talked about this a little bit in class today. So when the K value is larger than 1, that would denote that we have way more products than we do reactants, right? Because any K value is products over reactants, right? And so if we have a K value that is greater than 1, then that means there's more products and there's less reactants. That if we're thinking about a reaction going from reactants to products, that this did occur, that some of these were consumed and then some of those were produced, that this reaction did in fact happen. And that would mean that our delta G is negative, that it's thermodynamically favorable. Well, what about the opposite from this? What about when our K value is less than 1? Less than 1. Okay. And so here is where products over reactants, that we have way more reactants than products. That very few to none, like very few of these reactants actually turned into products. They mostly stayed as reactants. So it's as if this like reaction did not occur. And we know that that would be not thermodynamically favorable, or delta G would be positive. Okay. I will say that this is kind of that line, which is 0, that we don't get a negative K value ever, but our line of comparison is at 1. So is our K value greater than 1, or is it less than 1, but it will not be negative. Okay? So when a K value is bigger, if it's bigger than 1, then we have a negative delta G. When it's less than 1, then we have a positive delta G. Alrighty, so for certain reaction, delta H is negative, delta S is negative at 25 degrees Celsius. Which of the following statements provides the best description for a system at equilibrium? Okay. Alrighty. So we have 2 negative values. And so I wonder if this is going to be thermodynamically favorable or not. Let's figure this out. So we have delta G is equal to delta H minus temperature times by delta S. Okay? And so we're solving for delta G. I want to know if this is negative or not. And my delta H is negative 20 kilojoules. Oh, please, please, please check your units. Kilojoules and joules. Let's convert either this to joules or this to kilojoules. Let's go this one to joules. Either way's fine though. So it'd be negative 20,000 joules. Okay, great. And now we're going to minus the temperature, but temperature in Celsius and temperature in Kelvin. So we need to add 273.15. So I'm going to do that really quick. So 25 plus 273.15. And so this would be 298.15 Kelvin. And I'm going to times that by negative 400 joules per Kelvin, right? So this whole thing multiplied. Kelvin will cancel, and we're going to be left with joules. Okay. So this number times by negative 400, this is going to be minus 19260 joules, and we have negative 20,000 joules minus this. Okay, so this is definitely going to be a big negative number, right? That we have this value minus, oh wait, I apologize. It's minus this negative. This is going to be positive. So this number times by that number is this negative value, and then it's a double negative here. Okay, so this is going to be a big positive number. So we're going to have so delta G is equal to a positive 260 joules, or 99.26 kilojoules. So if we have a positive delta G, then that means that we have a K value that is less than 1. So we're staying close to our reactants side. We have way more reactants than we do products. So the system contains mostly products? No. The equilibrium lies close to the middle? No, that'd be like at 1, right? The system contains mostly reactants? Yes. The reaction goes to completion. I mean, all the reactants turn into products. No, that definitely did not happen. All right, good. Let's do, actually, that's her time. That's her 30 minutes, and I'm not going to go past that. So then class time, we will do a few more. All right, thank you all.